All right, welcome to week 5, which is our registration and calibration week. This is a class of a lot of math without having to do math. So I'm going to be giving you a lot of equations, a lot of formulas, but the key thing is that we talk about what each part actually is and what it's doing. So there's going to be a lot of discussion around that. So don't get hung up on the math. Don't get hung up on like all the different symbols, but know what the different components are. And the purpose of the formula is to really just show you how they're all related. So I'm going to start with registration and talk about that. Really, we're talking about geometric models to how do we get X, Y, and Z values from a LiDAR system, right? So this is how do we get those real world coordinates for that. The terrestrial laser scanning one comes later. It'll be the last of the PowerPoint lectures, and we'll talk about that one. That one's a little bit different. This one we have to take into account all of our different systems. So starting off with that, we have our rotations. So as you recall, we have rotation matrices. There's lots of them, lots of need to worry about 3 dimensions, right? So every single system that we have that is in Airborne Lidar, that's the GPS, the IMU, the laser scanner itself, the bore of the laser scanner, which is where the light actually shines through, the like WGS84 coordinate system. We have local coordinate systems, which is how the light interacts with the target itself. So there's a ton of stuff, like a ton of different coordinate systems that we're dealing with here. And we have to rotate them all to put them into a single coordinate. Like there's translations as well. But this is just reintroducing what these rotations look like. So each of these angles is our rotation angle. And then n is a vector at that axis. So we're including a little bit of the unit vector with that axis. So we are, as you can see, there's lots and lots of components. You guys have seen something similar to this before, probably in, you might have seen it in control surveys, but you definitely would have seen it in geodesy and definitely in least squares or adjustments class. So there's your rotation matrix. I'm not going to spend a lot of time on that. You have seen them before. I'm bringing back nightmares. You guys are going to not sleep well tonight. But you don't have to do any math with them. Just showing you that X, Y, and Z are important, but they are all connected in some way. There's some sort of dependency on each axis. So that's where these 1, 2, and 3, those are the vectors about each of the axes. So we have to, it's like our weighting. Okay, so this is our coordinate systems. We have quite a bit happening here. So we have our Earth fixed system, we have our INS, we have our GPS, we have the scanner frame, we have our local coordinate system down here. We have different vectors that are in between here in rotations. So for example, here we can see that the X going from the B frame, or going to the B frame from the E frame, backwards, sorry, I'm following the arrow, going from the B frame to the E frame. So there's a B frame, there's the E frame, that's the 2, or sorry, the from is on the bottom, the 2 is at the top. So here we can see that we go from P, which is my point, to S, which is my scanner. So again, how do we go from here to the scanner and translate that information to that location? So we can see here that the scanner with position is related to rho, which is my range, and nothing in the X, but in the Y and the Z for angles. And here's our angle, so off of this Z axis here, and this one. Okay. So, and actually, I'm going to go back to that and refer to this again. So looking at this, you can see that the X direction is 0 in this case. Now, why is that? because we're looking at a three-dimensional system, but why would my scanner only have 2 dimensions? And really, that is what airborne laser scanning is. It is only a 2-dimensional scanner because it doesn't actually go around in 3 dimensions. If you think about the rotating mirror, oscillating mirror, that as the light comes, it's really only pushing it in one direction. So you're creating a line. A line is only 2 dimensions. It's not a 3-dimensional thing. If it was 3 dimensions, then it would also push it forward. So you would have like a full circle in that case. But going back to here, we consider airborne laser scanning to be a 2-dimensional thing, 2-dimensional scanner. That is why there is nothing there. So that just explains that component. So let's look at these frames. There are different types of frames, and we usually refer to them just merely as their initials. So the sensor frame, or the S frame, is the actual sensor itself. It's the laser scanner. It is a 2D scanner, as I pointed out previously. And the target itself is related to the scanner. And that scanner is expressed by the range and the angle from that scanner. So we take the point, figure out the range, we know what the angle is based on the point when it was sent out, and we can figure out where it is relative to the scanner. It is a Cartesian right-handed system, so we start right-handed with the sensor frame. Then, kind of bouncing around here, we have the Earth Center Earth Fixed frame, which is the E frame, also known as you could just call it the Earth frame. This is what the GPS and INS rely on. So they're based on the center of the Earth. It's a geocentric ellipsoid, also known as WGS84, that we often use. The x-axis is the Greenwich meridian, the z points in the mean direction of the rotational axis, and y makes it a right-handed system. So the sensor frame is not directly related to the Earth frame. They are separate, and they have no connection other than like the sensor to the point, and then this Earth-centered Earth fixed frame is related to the GPS and INS. So our next frame is the local level frame. This is the point on the ground. So on the ground, we're looking at like an incidence angle is what it comes down to. And so the incidence angle, or looking at the perpendicular from the tangent of the Earth's surface, we're developing our local level frame. So what we use this for is to orient the GPS and the INS system based on what the Earth is doing, the Earth's surface is doing. The origin is arbitrary, so you can put it anywhere. Generally speaking, we'll put it where the point, or wherever within that point cloud we want to set it. It's a local relative frame, and we put it on the Earth's surface so that it's either pointing up or down. So we have our LNED, or an LENU. LNED is where it points north, so the X is north, the Y is east, and the Z is down. Or we have the ENU, which is the east, which is our X, then north, which is Y, and up, which is the Z. So usually the LNED is the most common. We'll use that one. So pointing into the ground, it's like towards like the geoid. And they are both right-handed systems, so if you use your hands and try to figure that out, like the up and down, you should be able to get that to be right-handed for both of them. So the local level frame is all about the Earth's surface and where that airplane is with respect to the Earth's surface, or actually it's not the airplane itself, it's actually the sensor. But the GPS and INS can also be related to the surface of the Earth. And will relate back to those, so they do connect. The next thing is the body frame. So the B frame is the air carrier. Another right-handed system. It determines the relative orientation of the attitude of the carrier. So we're not talking about whether it's grumpy. We are talking about the yaw, pitch, and roll. And so the body frame is our INS. It's centered at the INS system. And this is a really important system because it tells us where the airplane is in space, right? So, and how it is pointing with respect to its flight. So the B frame is the airspace location. Then we have something called a mapping frame, which is the projection, so sending data to another datum or projection. This is not actually on our diagram, so if we go back to the diagram, it's not actually on there, but what it does is it takes this E frame and projects it into another frame with a different coordinate system. So it's looking back at this. So we have our Earth frame, which is the center of the Earth. We have our B frame, which is the INS. We have the scanner frame, which is the S frame, and that those two are related by this radius. We have the local frame, which is down here, which is just that 90 degrees to the Earth's surface. Our point falls here, so it is with respect to this arbitrary system, but we can also project it up to the scanner, and we tie all of these together in a single equation. And that single equation is known as the Airborne Laser Scanner Observation Equation. You do need to know this, but not memorize it, okay? So how does everything tie together? So we start here with, we're trying to calculate this. We're trying to figure out what is the point with respect to the Earth frame, right? We want to get to real world coordinates. Where are we located? Where's every single point in my point cloud located? We have to calculate this particular observation equation for every single point. So you can imagine the mathematics and the computing power that goes behind doing billions of points in a single project. So the first thing that we have here is a translation, right? X is going to be a vector, so a translation vector. We go from the B frame to the E frame, right? So we're looking at the INS and taking that to the Earth system. So we're shifting that one down to that location. Then we take our rotation, so the R is referring to rotation, and we go from the local frame to the Earth frame. We shift that into there. So that takes our astronomic coordinate systems here, latitude and longitude. Right? And then we take our body frame and we project it into the L frame. So we move the INS down to that local frame, and we look at the raw, pitch, and yaw at those times. Everything's respect to time, right? Because everything is time related in LiDAR. Then we have the scanner to the body frame. Notice that there's no time with this one. The reason that there's no time with this one is because the scanner frame and the B frame, they don't move with respect to each other. They are in the exact same line. They are secured onto that airline. And when you look from the scanner to the B frame, when you connect those two together, there is no change in time. They're always going to be the same because that line doesn't change. Then we have our B frame to the S frame. So we're doing the translation. So shifting it over, we have our range with respect to time for each point, and our two-dimensional scanner that is included there. All of these tie together with all this math here. We tie it all together and we create our point with the Earth fixed system. So that is the observation equation. We are trying to, every time we're trying to get it into the Earth fixed system for every single point. So you can imagine the math behind that. So another thing that is considered is this trajectory by the GPS and INS. Because if you think about it, when the sensor sends down its data, it sends and then it receives. After it has sent down the laser information and it is returning back, we have a change in time. So timing that GPS and INS to collect the data by the time that it has been sent and received, and it sends out, so and the airplane's continuing to move, so we have to, the GPS and INS have to predict where the airplane is going to be as it's receiving the data. So we do use Kalman filtering, which you may have heard this term before with your other classes, or you will be getting into it this semester a little bit. And we use that to integrate the two sensors, so the GPS and the INS. The biggest problem is that the INS does have a fair amount of noise, and of course GPS has a lot of error in itself, even with differential GPS, because we have a moving object. So we try to contain those errors as much as possible. And then we have filtering limits. We don't have filtering limits. The filtering that we do limits the errors of the INS. So we smooth it out. We smooth out all that noise as much as possible. And we try to reduce down all the systematic errors as much as we can. So once we have taken care of the GPS and INS, these are kind of like separate from the laser scanner, but they are still an important component to the error and the measurement uncertainty within our LiDAR data. So that means that we need to start looking at other things. So taking our observation equation, what are the errors that we can see through that observation equation? So then we've developed something called a general error model. This is the general error model. Again, you don't need to memorize everything. I'm going to go through it all. So I'm going to go through each component that is of greatest importance. So we have GPS and positioning errors, we have orientation errors, we have bore sight errors, we have the installation matrix, which is like when you install stuff onto the airplane. We have a lever arm error, that is the distance that you calibrate between the sensor and the INS. Then we have ranging errors, we have misalignment errors, we have encoder errors. Everything adds together. We use the error model so that we can reduce the systematic errors that come out of this. So modeling, we might have a very large number, but we can now remove that from the error, right? Or at least reduce it that much from the error. So that's why we build these. So I'm going to go through each of these components here, which is not like, again, knowing what they are is more important and kind of where they sit in the equation. So the one sitting at this end, like this delta x hat with the body to the E-frame, this one has a higher impact than something on this end. All of these rotations will impact it all. So generally speaking, anything at the beginning of the error models have a higher weighting than anything at the end. So looking at this biggest one, the trajectory positioning errors. I just finished talking about trajectory, trying to estimate that. We're trying to deal with the GPS and the INS. We're trying to handle all of those errors that are happening with that. We apply Kalman filtering to try to reduce those positioning errors. We still have errors. It's just the way life is in any kind of technology. So we have to worry about DOPs, right? The DOP values are really important. Every time you go out, even with a handheld GPS, you kind of want to know what your DOP values are going to be because you could be 100 meters out. The signal observability, so what satellites are available at that time? Now, generally speaking, that shouldn't be too big of a deal, but it's still something to keep in mind. We need to observe the accuracy of everything, right? So what is the GPS error sitting at? What is the INS error sitting at while we're working on this? Then we're looking at baselines. So anything less than 10 kilometers is considered a short baseline. We are working with short baselines. And so with those, we have our general GPS errors with short baselines, which is the troposphere, ionosphere, multipath noise, and orbit error. So we add all of those up, let's just say with the maximum amount, we end up with about 4.1 centimeters of error just from GPS. So you think, well, my RTK gets better than that. Well, yes, but you're also not on a moving airplane, right? So this is actually pretty good, and that's still like a high error, but these errors only include these 5 errors from the baselines. Then if you do have longer baselines than 10 kilometers, you do need to have post-mission processing, so post-processing, to be able to try to adjust these positioning errors. So the INS, it does help lower the errors in the GPS, but it still has its own errors as well that contribute to it. So getting into that, that's where this is the orientation errors from the INS. So they come into play. So you have your platform that's vibrating. You can denoise the INS to say, okay, we're going to get rid of this vibration in the data, which allows us to be a little bit more accurate. And once you've denoised it and like smoothed that out a little bit, you can have your you can determine the attitude of the platform. And then, but our errors are still within, you know, a few like decimals of degrees, right? So this is all in degrees, so 0.1 degrees at the most is the error from the INS. So the scanner itself has two types of errors. One of them is the range, the other one is the accuracy, or the accuracy of the, it's the accuracy of the angle. So the range accuracy depends on the time differencing. Time errors are a big deal. Just think back to the GPS time errors, same idea. We usually end up with about 2 centimeters of error with the range accuracy. Then we also need to correct for atmospheric refraction, because that happens. Refraction affects the angle, it also affects the range, so that's another thing. We also have intensity issues, so hey, what about, you know, when we end up with speckle from a rough surface? That's a big deal. Then we have scan mirror shifts that cause an angle error. So this happens within the scanner itself. If the mirror shifts, then we can end up with, you know, up to 4 centimeters of error. Generally speaking, this shouldn't be too much of an issue, but sometimes it is an issue. so it's something to be aware of, and that is all within the scanner. That's something you'd have to take it into the manufacturer to get recalibrated and adjusted. Another error that happens with scanners is going back to the physics of lasers. So divergence of the beam. So looking at the beam diameter it's an error, right? So we know what we do is we measure the center line of the beam width, and that is considered the center, or the actual measurement that we pick up. That's what we for timing. But if the beam diameter is larger than what it needs to be, and it gets bigger and bigger and bigger, we use that standard deviation to give us the error. So it's about 1/4 of the beam diameter. And so if your beam diameter is 10, then that means you have about 2.5 centimeters in error. So that just kind of gives you, well, the standard, that'd be the standard deviation of the beam diameter. This shouldn't be that big, right? Your standard deviation of your beam diameter should not be 10 centimeters. But I'm just giving you a quick number there. So generally speaking, the footprint on the ground is about 10 to 15 centimeters in width. Another error that we have is the lever arm error. So we are looking at positioning and alignment between the sensors. So when you go in to do the close range surveying on the airline, you need to be very careful with this. And if there is an error, it's going to come up here. So even then, like, you're still using equipment to measure distances and angles. So again, you're going to end up with some errors, right? Because the equipment itself will always insert more errors into your calculations. So this diagram here is just showing you kind of all the stuff that can happen, the rotations and like the different coordinate systems that we have to deal with, and trying to align them. So these they call them level arm there, but they're lever arms, we call them. So the lever arm and the lever arm, and if you have a camera, lever arm. So how do we measure all of these within a very tiny space? And it comes down to close range surveying. Then we have a bore sight error. This is how the scanner actually scans through the lens. So as you know, a lens can, if things are not perfectly lined up within the scanner itself, it will cause an error. So this, because it's relative, and what I'm saying here, it's a relative error between the IMU and the laser scanning plane. So that means that everything could be placed correctly, but it's the error that means that, okay, when the bore sight is supposed to be pointing straight down, perhaps it's out by 3 seconds, right? So that 3-second angle, if you project that over 600 meters, that can add to a larger and larger error every time, right? So just how the laser goes through the lens is my bore sight, and how that is actually related to the IMU is going to the angles of the IMU now have error, built-in error, because they're not being represented as they should be with the exact 90 degrees to everything. So if you do a cross section of a surface, you're going to find that you'll see the roll, pitch, and yaw, the roll and the pitch, because that's what this contributes to, is all 3 of these errors. But the yaw errors you're not going to see. So you can try to reduce down the roll and the pitch errors, but the yaw errors have to be dealt with in another way and minimized with other mathematics. So the scanner assembly, this is misalignment between the encoder and the mirror rotation angle. So again, a lot of timing that's involved in this one. And so it's also known as a pitch slope error, because that's where you're going to see it. You're going to see it in the pitch. You can mix this up between the bore sight error, so it needs to be separated. The reason being is that this misalignment is a manufacturer's error. The other one might be just merely a screw is loose, right? So you might be able to adjust for that one. So our actual target, what does this whole error budget look like? So how do we kind of break it down into its pieces? So we have angular uncertainty that's amplified by flying height, right? So every time I get higher up, then we end up with more and more uncertainty in angles. The IMU and bore sight actually contribute to 60 to 75% of the horizontal error. So this is our XY direction on the ground. So if you're seeing a big error, it's probably something to do with the IMU or the bore sight of the scanner, or even the placement of the bore sight of the scanner. Attitude errors, so this is the vertical error. Anything to do with yaw, pitch, and roll, those ones all contribute to about 25 to 50%. But if you are using a helicopter, the vertical error equals the scan angle error. So it ties back to that. And usually you can get that relatively quickly through your mathematics in the software. So the software will do that for you, and you'll be able to get that information. So there's a lot of errors, but the bulk majority of them are dealt with the IMU, the bore sight, and yaw, pitch, and roll, which the attitude errors all tie back to the IMU. So the IMU can cause a lot of problems. So just like thinking about the scanner geometry and how these errors really propagate. So if we have a vertical error, so we can see that the point down here is what we really want to measure, but we can see that sometimes these vertical errors can happen. So, and then we also have horizontal errors that go back and forth within that beam width. So we can see that we can end up with some pretty strange values, and they can really fall like anywhere in these boxes, right? And if we draw the whole thing, it could fall anywhere within that whole box. So the bigger these are, the worse it is. And of course, within the beam width itself, going from one end to the other, we can end up with even larger values, like larger errors, just because of that beam width. So if we have a high incidence angle, we can have higher accuracy degradation, which means that as I'm pointing further and further away, so we can see this angle here, this down here becomes bigger and bigger and bigger, which means that these errors get, this box here gets bigger and bigger and bigger as well. So it does contribute a lot to the error if we are not trying to get it close to the nadir and if we're scanning too wide. So the field of view is really necessary to keep it as narrow as possible to avoid this issue. So next on the list is like truly the registration and looking at the E frame to the M frame. And so there are a couple things that we can do with this there is, once you've got your data in the E-frame, then you can apply your map projections and project it into another frame, an M frame. Now I have a couple of frames here that I have mentioned on this page. We have the N frame, which is the national frame, and G frame, which is a geoid frame, or ground frame. I've seen called ground frame, but it's really the geoid frame. And so between the two of them, national is just another way of referring to mapping frame. It's just specific to, most American textbooks will say N frame because that's what they use, is they have their state planes and national coordinate system that they use a lot. We just use a mapping frame, so we can use that. So just M frame is fine here. The G frame is the geoid frame, so now we're taking it from the ellipsoid and we're moving it onto the geoid surface for height. So that's the next thing that's great fun, right? So all the stuff that you guys did in map projections, this is really what happens. And so I've included everything here, that what it looks like. So we have our translation from the E frame to the N frame. We have a scale factor to the N frame. We have a rotation from the E frame to the N frame, and then the point itself to the E frame. So this is the full transformation. I'm not going to get too hung up on this. You guys did a whole course on map projections. So this is it's just important to know that the registration of airborne LiDAR really comes down to projecting it into like a mapping frame and then shifting it to the geoid frame. And then everything should match together. Like everything's already georeferenced. So the registration component of it should be minimal. It's only if you have extreme errors in your strips that will cause problems. Otherwise, it just comes in and is already georeferenced. So the strip adjustment, this is when your strips don't match. What you would do is you'd have to go back out, fly out again, and do additional strips. So when you do a strip adjustment, this is just like doing a block adjustment in photogrammetry. So, which I think you guys do this semester. So if you have your overlapping and cross strips, which means you have your regular strips that you were doing, and then what you would do is go back and like do some that are 90 degrees to each other. If you do that, what that does is it allows for all those strips, even if it has one strip that is at a weird angle, like this one doesn't match, you can say, okay, well, now I'm going to have another one that goes maybe this way, and it's going to tell me whether it's the red or the green that is correct, and will allow me to shift this particular one or this one to the correct location. So we want to estimate the global shift and rotation between the individual shifts or strips. So that's what the goal of this matching is. And because it's already directly georeferenced, bringing it into this is really just adjusting errors. So it's like reducing down your RMSE value, right? We do need sufficient side lab for identification. Because if you only have 10%, that's kind of the bare minimum. You might want to increase that more and go with additional side lab. So maybe you might want 20%. And then that helps with trying to adjust for these strip issues that you'll see, these misalignments or this misalignment from there. So registration is fairly straightforward, a little bit more complicated when we get to the terrestrial laser scanning, and we'll talk about that when we get there. And last but not least, we're going to talk about calibration of these airborne scanners. So it's not a big topic, it's just one slide, but just to kind of keep this moving. So the system calibration, we have to use, like for range, we need to have close range surveying to determine the length of the lever arms. So this keeps our INS, your GPS, your sensor, all well tied together. And then knowing those distances, you can set the timing and adjust the time for for synchronizing them together. Then there's orientation errors as well that can be calibrated through the in-flight procedures. So these are mostly the orientation of the airplane, but also the angles that you get those lever lengths, those lever arms, within the actual airplane itself. And then you got to figure out those angle errors as well. So when we do in-flight calibration, so you have to actually get up into the air to calibrate. And you would normally do your calibration in the airplane, then you would send up the airplane to calibrate, and then you would fly your circuit, right? That is how you would calibrate your system to ensure that nothing has gone kind of haywire on you. So we do like to use terrain to check it out, or control points. Control points are really helpful. We use them quite a bit as well. You can get targets for it. We also have building profiles, so rooftops are really good because they're pretty standard, they're pretty flat. So you can check out like, oh, okay, you know, looking at this long building profile, I know that this is the angle that it should be at. Also, when you go back and forth, like in different directions, then a building should be a building, right? It should look like a box. If it's fuzzy, then we know that there's a problem with the calibration. So there are semi-automatic, manual, stripwise, and global methods. These are all different types of in-flight calibration methods, but they all require a lot of people work. You can't really repeat them every single, so it's not even something that you can be like, okay, well, you know, I'm using the exact same setup as I did yesterday, so everything should be the exact same, and you can't even do that, because if it's the next person, they may not have enough information and it may not work to calibrate it using those same numbers the next day. There is also no way to statistically check your calibration, which is not a good thing, right? So if you have no stats on your measurements, then you're kind of taking things at face value. So it takes away from that, the reliance on that, and that's not good. And last, we need to automate the process. So because of that, because of all these issues of these like other types of methods, we need to have this automated method. It allows us to get up there, get this calibration done really quick, and get flying, because using an airplane is always very expensive. So we need to correlate our GPS with the bore site, and so the rooftops are really important. And if you can do the rooftops, find an area with like kind of standard rooftops and fly over there, and you can fly in 4 different directions. And if the rooftops are showing up as rooftops and they're not fuzzy and they're not shifted around, then you are good. And the computer can identify that. So this is all stuff that's happening on your laptop when you are in air. And then once it's calibrated, then you can get out and start scanning. So, and using our wonderful observation equation in order to get your data points. So today's class was all about registration and calibration, talking about the geometry. What is the primary thing that we are trying to identify in LiDAR? So we know that the LiDAR observation equation is what ties everything together in terms of getting our information to a Earth-fixed system rather than just the scanner itself. And so that's really complicated, and because of the complexity, we have a big systematic model that we have to use to try to reduce our errors. And using the error modeling, then we can identify the different components of the LiDAR equation. And even then, like, you may not need to adjust for every single one of them, but some of them might be required. And then from there, all those different parts, all the different components, all the rotations and translations that come together to move that point in space into the Earth center, Earth fixed system. Then once we've got that, we can register our data, which hopefully nothing is a problem, like strip and require a strip adjustment. If our strips are all nicely lined up, everything is georeferenced correctly, then all of our data points will come together without any need to do much more adjustment. But before we do all of that, we have to calibrate. And all those calibrations start at the very beginning. And we just include all of the calibration data into the flight information. So that is probably the last of the very technical information that I have for you for this semester in terms of airborne LiDAR. Next week, we're going to be getting into, I think we get into feature extraction. So once we get through feature extraction, then and then it gets into quality control, and then we talk about terrestrial laser scanning. So we're almost there at the end of this, of the theory component of this course. But again, listen to this video a few more times. I would normally have you guys doing a lot of activities in class to try to get the concepts. Again, I don't have that option this year, but I look forward to seeing you guys next week.